Hello, hello. So, example 9.4, pause and copy, pause and copy, pause and copy. Okay. So, we're going to revisit our model. Our model right here. So, I'm going to do it for this obviously fictional scenario where I have 365 hospitalizations, and then 3 weeks later, I got 1410. Okay, this yields, after some work, a function here. And now let's see what happens when I plug in t equals 10 weeks. 10 weeks after April 1st. What do I get? Well, nothing good. Pause and copy. So as you can see, when I plug in 10, I get over 32,000, which is impossible, since my population is only 5,000. Okay, so there's something very wrong with this model. Okay, it doesn't take into account certain limiting factors. It doesn't take into account a lot. We're doing fairly simple modeling here, but it certainly doesn't take into account my population size. So let's improve this model and go back and fiddle with this differential equation here. So this differential equation here is saying that the growth rate of my population is proportional to the size of the population. Now, that means it's just going to grow and grow and grow and grow and grow with no upper bound. Okay, this is a very, very simple thing. So let's make it a little bit more sophisticated let's see. So what we'll do, we'll pause and copy. What we'll do is we'll take our original model, which is here in the green rectangle, and we'll add this factor here. What does that do? Well, notice that M is my population, total population, and notice that if, say 4,000 people are hospitalized, then this fraction here is going to be close to 1. So this bracket here is going to be close to 0. And what that means is that my growth rate is shrinking. Okay, my growth rate is smaller than it would be if y were, say, just like 100 or something. Okay, so I say it here with my notice thing, but I just said it again out loud. Okay, this factor makes my growth rate shrink as y gets closer and closer to m. Okay, we're going to call m the carrying capacity. I'll repeat this below, but okay, now we can solve this more complicated differential equation and get a more sophisticated model. So we're still doing fairly simple things, but I hope it gives you an idea of how this works in practice. You set up a differential equation that somehow reflects your physical or natural phenomena. And if you choose a simple enough one, you can solve. Okay, so what do I do? Okay, so pause and copy. Start by separating. Okay, so I separated and I integrated in one step. So separate plus integrate. I did two things in one step there. So this circled thing in green came downstairs on the left-hand side, and I integrated both sides. Then what I do is I multiply this fraction, top and bottom, by m, and that simplifies this integrand here. Now, if I look at this dude here, I can actually do partial fractions there. I'm not going to show my work, but this is what happens. Now I can integrate both sides. And let's see how much we got here. Okay. Now I can integrate both sides. And a whole bunch of technical steps. Pause and copy, sorry, if you haven't done so already. This one's a bit strange. What did I do? I wanted to flip this fraction. So flipping that fraction brought a minus out here, but I brought that minus over to the right-hand side. I have an absolute value here, but it can disappear just because I notice that this fraction here is, in this case, positive. You can see it right here. Okay, m is bigger than y. So you got something bigger than 1 minus 1. All right, that allows me to not worry about this absolute value, which is a nice thing. Okay, soldiering on. I eventually arrive at this formula here for my population. So pause and copy that. Now I want to find A and I want to find K. So above I had this line. So I'll copy it again down here. Plugging in t equals 0 allows me to quickly find C. T equals 0 and y is 365. Then I can remember the relationship between A and C. Or if you want, there's a formula for A, which you could memorize if you like. Now what I'm referring to, this is y. This is the function y with 0 plugged in. Or you could say this is the, in our case, this y of 0 is the 365 over here. And the m is, of course, 5,000. So that gives me A. Do some more work to find K. Pause and copy that. What am I doing here? I'm taking this line again and plugging in this point here. It allows me to find K. All right, now this gives me, finally, a much more reasonable model. Given here in symbols, I have A, it's above somewhere. I have K, it's right here. M is 5,000. Okay, so now after 10 weeks, this model is going to give me a much more reasonable result. So here's what the graph would look like. Now you can see that at least initially, maybe for this part, you can see it looks exponential. But as I go further in time, the graph flattens out and it eventually approaches this horizontal asymptote 5,000. So pause and copy that if you haven't done so already. Okay, so again, we've taken a very, very simple model, which was our exponential model, and we modified it to get something which takes into account a sort of ceiling on our y. In this case, that ceiling was the 5,000. Okay, some vocabulary here. Pause and copy. So this differential equation. Remember, it's just the exponential growth, but then you have this extra factor here. This is called the logistic differential equation. M is called the carrying capacity. And we also have something called the relative growth rate, okay, which you get by taking the growth rate and then dividing by your population. I'll give you an example to show you what this growth rate in vocab mean for us. So I'll pause and copy all this. So in the logistic model, the relative growth rate is proportional to this shrinking factor here. And I hope this statement brings all the vocab together in a way that is at least clear. So here we have the relative growth rate, which is, again, the growth rate divided by y. Okay, so it's the growth relative to the population size at any given time. So in the logistic model, this is the thing that is kind of going to zero. Okay, you'll notice that y is getting closer and closer to zero. Oops, y is getting closer and closer to m. So again, this factor is going to zero. And that is what causes our curve up here to flatten out.